Welcome back. In today's lecture, we are going to see that how to tackle constraint optimization. Okay, and obviously, I am going to extend the previous result, which we have talked about the finite dimensional unconstrained optimization. So in today's lecture, I am going to limit myself only on the finite dimensional constraint optimization. Okay, and in the later part of this course I will also talk about the constraint and unconstrained optimization and what kind of technicality involved during the proof, okay, in case of the infinite dimensional optimization. Okay, so let us come to the problem formulation. So problem formulation remains exactly same like the previous class. Okay, so I have some kind of function. Okay, and I am assuming that this function is mapping from Rn to R. It means that this is real valued function. Okay, and after that, and here x, you can think like this, x1 x2 up to xn, like this. Okay, so I have n tuples of the real numbers. Okay, that is the argument of this particular function. Okay, and what I am going to do now, I am going to assume that d be some subset of Rn, and in the best case it might possible that we are going to consider the whole Rn. What does it mean? That I am going to talk about the minima or maxima. In today's lecture mainly I am going to concentrate on minima, because we know that how to extend same result if maxima comes into picture. So I am not going to look minima in the whole domain. Okay, I am just going to look in the subset of the Rn. Okay, so I have whole space. Suppose that if you are in three-dimensional space, for example. Okay, so I am not going to concentrate on whole three-dimensional space. We are just going to concentrate on some part D. That is the meaning. Okay, so now whenever we are going to talk about constraint optimization, obviously I have some kind of restriction, I have some kind of constraint. Okay, so in order to minimize this function, okay, we have to also give guarantee that constraints should not violate it. Okay, so in the previous class when I have talked about the unconstrained optimization, at that time we don't have to worry about any kind of constraint, so we are very much free. But here we are not free. Okay, we are going to understand what is meaning of free in the next slide. Okay, so let us first define the constraint, and in this class I am just going to talk about equality constraint. Equality constraint means whatever constraint that comes into picture that equal to some number or something. Okay, that is not going to express in terms of the something less than 0, greater than 0, less than equal to 0, or like that. Okay, so what I am assuming, suppose D is a surface in Rn, so I am going to consider this as a surface defined by the equality constraint, and equality constraint suppose that is defined like this. Okay, and here one more assumption, what I am assuming, that whatever equality constraint I have, h1 h2 and hm all are at least one time continuously differentiable. Okay, and again that will map from Rn to R, same like the main function. Okay, so in this way we have defined the constraint. So I have equality constraint. Okay, I have some function, and that function, and I know that somewhere in this particular region D there exists a minima. Okay, now we are going to find some kind of necessary condition such that I can able to check that if that condition is satisfied, then there exists a minima. Okay, so that kind of result I am going to develop. Okay, and obviously I am going to assume that f is continuously differentiable. Okay, and I have to study minima over D. I have already told about this. Okay, now let us try to see that this first order necessary condition, again, whenever we are talking about first order, you know that I am talking about some kind of Taylor series expansion about neighborhood of the minima, and after that what we are going to do, we are going to take some kind of assumption that whatever first order term that comes into picture, that is going to dominate our all higher order term. Okay, and in the next part of this lecture we are going to see that how basically this necessary condition is related to Lagrange multiplier. Okay, so in another way it is possible to show that if we involve the Lagrange multiplier, then constraint optimization problem is converted into unconstrained optimization problem. Okay, we will see. Okay, but before seeing that, we have to give some kind of mathematical guarantee. Okay, so that part I am going to discuss. So x star belongs to D, be a local minima of f over D. So what we are assuming, that I have this region D, okay, and I have some function and I have some kind of constraint, and that constraint is basically given by h1, h2 and hx all equal to 0, so equality constraint. After that I am assuming that I have certain kind of minima, that minima is x star belongs to D, means in this region only minima is going to belong. Okay, one another assumption, we are going to understand this assumption not at this moment but later part of this lecture. What we are going to assume, that x star is a regular point in D. Okay, so whenever we are talking about regular point, so meaning of this, that if you take the gradient of the constraint, okay, so I have m number of constraint, and we know that m number of constraint everything equal to 0 up to, so this kind of constraint, so I have m number of constraint. So if you calculate the gradient vector of this all constraint, that is linearly independent. If that is linearly independent, then we can tell that the x star, where I have calculated this particular gradient, that is called the regular point. Okay, so anyone has confusion in the meaning of linearly independent, then please let me know. What is meaning of linearly independent? Bhavita, could you please tell me that what is meaning of linearly independent? Suppose I have 3 vectors or 4 vectors in some space. So how to tell that all are linearly independent? Bhavita, please unmute yourself and answer the question.
Yes, sir. The meaning of linearly independent means the function is independent each other.
What does it mean? I'm not talking about functions. I'm telling that okay, you have some kind of vectors. Okay, vectors may be function also. That doesn't. I'm talking about general vector. Okay, vector may be function, matrices, column vector, anything. Okay, so when so one thing is that, could you please just give me algebraic condition, and after that I will ask you the interpretation of that algebraic condition. So how to tell that I have something like some vector v1, v2, v3 that are linearly independent. Could you please tell me the condition, algebraic condition?
B, uh, then sir B1 and B2 which all are equal to 0. Like,
Okay, please check, Bhavita. You have to go through the linear algebra. Linear algebra is very important subject. Okay, so please go
okay,
through that, because otherwise you are able to see several terminology and you are not able to understand that terminology. Okay, and
okay, sir.
and actually I am taking one parallel course in bachelor student. So there I am talking about vector space, linear algebra, or the sorry, vector space means linearly independent, linear dependent, or span, basis, all kind of things I have discussed. Okay, so if you have any confusion, please look into that. Priyanka, could you please give me algebraic conditions such that v1, v2, vn are linearly independent? Priyanka, unmute yourself.
Yes, sir. Sir, it is equal to 1.
Shubham, Shubham Prasad.
Yes, sir. Good morning, sir.
Good morning, good morning.
Sir, I think coefficient of each vector should be equals to 0.
Yeah, linearly independent, then coefficient equal to 0. It means that suppose that if I have some kind of vector v1, v2, v3, so I can represent like alpha v1, alpha 1 v1, alpha 2 v2, and alpha 3 v3. So only solution of this equation, since v1, v2, v3 can be 0 and non-zero, okay, so only solution is that alpha 1, alpha 2, alpha 3 all equal to 0. Then I can tell that v1, v2, v3 all are linearly independent. Okay, from here you are able to understand also linearly dependent. If that is not 0, then it means that I can able to represent v1 in terms of some kind of vector alpha 3 by alpha 1 into v3. You can see that if anyone, at least one component is non-zero, okay, so suppose alpha 1, alpha 2, at least if I will tell that these two component, out of this component, suppose alpha 1 is non-zero and out of this is actually non-zero, then at least I can replace or I can represent one vector in form of other. Okay, whenever all equal to 0, then what happens that I am not able to represent one vector in terms of the other. Okay, so if I am able to represent one vector in terms of other, then that is called the linear dependent. Okay, if we are not able to do that, then that is called linearly independent. Okay, anyone has confusion? It means that whenever we are talking about linearly independent vector, it means that we are talking like this. You can think like this. Suppose that I have some space, okay, and I have to represent this space. So inside this space I have infinite many vectors. Okay, so most of time what is our intention? Our intention to find minimum number of linear vectors, such that linearly independent vectors, such that I can able to represent this whole space using that fewer number of vector. Okay, so at that time I can able to represent this space by infinite many combination. Okay, so any linearly independent vector if I will take, okay, and if I have two dimensional space, so any two linearly independent vector can represent this space. Okay, now what is our question, that how basically one can arrive on the minimum number of vector. Okay, so for that people are using the concept of basis. Okay, so basis is, whenever we are defining the basis, at that time we are actually checking two things: spanning the space, and second thing is that minimum number of vector. Okay, linearly independent vector. So suppose that you all are already well aware that if I select 1 0 and 0 1, and if I scale this by x and this by y, then I can move anywhere inside this plane. Okay, so whenever I am talking about linearly independent vector, okay, so using that span, it is possible to show that I can able to cover the whole space. Okay, so here you can see that what happens, I have that somehow I want to make sure that this constraint is always satisfied. Okay, so I am going to create some kind of conditions such that if I will generate some linearly independent vector, then we can give guarantee that everywhere that constraint is satisfied, like that. Okay, so we will see interpretation in terms of tangent space in the next part of this lecture. Okay, now I am assuming that here in this particular lecture we are going to use the concept of the vector space, subspace, linearly independent, basis, and also a span. Okay, so almost all concept of vector space is involved whenever we are going to talk about the proof of, or some kind of, whenever we are going to generate some kind of necessary condition, first order necessary condition or second order necessary condition for the optimality. Okay, so now here you can see that instead of line segment containing x, which we used in the unconstrained case, we now consider a curve d passing through x star. Okay, why this kind of things comes into picture? Suppose that you are in this region, and if you solve this constraint, then what happens? You come up with some kind of lower dimensional space. Okay, in this particular space, okay, I have some kind of lower dimensional space. It might possible lower dimensional means in best case I have same dimension like the previous one. So suppose if some space, this kind of space comes into picture. Okay, and suppose minima is here. So in the previous class, what basically we are doing, if x star is the local minima, then we are checking this side and this side, and after that we are telling by comparison that this point fx star is the least one in the neighborhood of this, in that way. Okay, so for that we are generating some kind of vectors like that, x star plus alpha into d. Okay, x star is the minima, and why I am telling x star is a vector, because I have considered this kind of real valued function, and here x is the argument and x belongs to Rn, and due to that reason x star, which is going to minimize this function, that is also belongs to Rn. Okay, and alpha is some kind of a scalar. I am going to parameterize it, and after that I have d. Okay, so a scalar multiplication I have defined, but d, whatever d I have considered here, so d is again some kind of column vector that belongs to Rn. In previous class we have already seen. Okay, so in this way linearly I can move from in this direction and this direction just by changing the sign of alpha positive and negative. But now that is not possible, because at the same time I have to make sure that constraint should be satisfied. And suppose that if constraint is like that, so if I move like this and like this, then I cannot able to cover, I cannot tell that this constraint equality constraint also satisfied. Okay, and due to that reason I cannot able to now define g alpha like this in terms of, because if you remember I am representing quantity like this alpha d, and after that we are telling that when alpha equal to 0, then minima of g0 and minima of fx star is going to coincide. So like that, but here it is not possible to do, because I have to make sure that both things should be satisfied. Okay, now due to that reason we have to make sure some other curve, not some kind of line. Okay, so I have to make sure that there exists some kind of curve which will satisfy both things, and due to that reason now you can see that g alpha I am defining in the general way f x alpha. Okay, so I have parameterized again everything in terms of g alpha, and again here I am going to make sure that when x star x equal to x star, at that time this g equal to 0. So alpha equal to 0 means x0 is equal to x star. Okay, so whenever I am going to make some kind of arbitrary curve, at that time I am going to make sure that this arbitrary curve is x alpha, but at the same time I am going to make sure that x0 is nothing but x star. Okay, and g0 equal to the that minimum point. So that kind of things I am going to ensure. Same kind of things I have written here. Such a curve is a family of point x alpha in D. Okay, and why family of point I have told, because x, you can see here x belongs to D and D is the subset of Rn. Okay, so this is not a scalar quantity, this is a vector quantity that belongs to D, and I am going to parameterize using a scalar. I am assuming that alpha is a scalar, same like in unconstrained case, but here I am going to consider general curve, general family of curve, but I am going to make sure that x0 equal to x star. Okay, at that time that is obvious, because when I have considered like x star plus alpha d, at that time if I am keeping alpha equal to 0, then automatically you can see that, or you can think like this: x alpha I have defined like x star plus alpha d in the case of unconstrained. So if you put alpha equal to 0, at that time automatically x0 equal to x star. Okay, so same kind of things I have just generalized it. Okay, so I am telling x alpha is general curve which is exactly equal to x star plus alpha d in case of the unconstrained. Okay, so in this way I have constructed. Okay, and after that what I am going to assume that x star is continuously differentiable. Okay, at least for alpha near to 0. Okay, so I know that f is actually whatever function I have taken, that is continuously differentiable. Now you can see that I have to construct x alpha which pass through the minima. Okay, so family of curve that pass through the minima, and that should be also continuously differentiable. Okay, so I cannot able to free to choose any kind of curve. Here that kind of condition is automatically obvious whenever you are defining like this. So you can see that this is differentiable with respect to alpha. X star is some kind of constant point, and d is some kind of vector, so you can able to define differentiability with respect to alpha. But here if you are going to give generalized construction, at that time some assumption is required, and which is also consistent with respect to unconstrained case, and due to that reason this assumption comes into picture. Okay, and I have already told you that now I am going to consider some other curve, and that curve is basically now I am going to take, that is nothing but g alpha equal to fx alpha. Okay, so this kind of parameterization I am doing, and you know that why I am doing parameterization, because if something is a scale in terms, if something is represented in terms of the scalar, okay, then it is very convenient to apply the result of means classical calculus. Okay, and due to that reason I have parameterized everything in terms of alpha. Here alpha is nothing but a scalar. Okay, so I hope that you are able to understand the all kind of assumption. Assumption is very simple. I have some function fx that is going to basically represent, or that is going to lie in some region D. Okay, after that I have constraint. I am assuming that gradient of each constraint are linearly independent. Okay, after that what I am during parameterization I am going to assume that x0, if alpha equal to 0, alpha, using alpha I am going to parameterize, so alpha equal to 0 gives us x star, means minima. Okay, and whatever family of curve x alpha I have considered, that should be continuously differentiable, and then I have constructed curve like this. Okay, so in this way I'll end up to here, and in the next slide I have taken when no inequality constraint, then obviously in place of this curve that I have written fx alpha, I can able to replace everything like this by in simple construction x star plus alpha d. Okay, and I hope that you are able to understood that why this kind of construction is not possible in case of constraint, because at the same time I have to find the minima, but I have to make sure that all constraint also should satisfy. Okay, so extra actually assumption that comes into picture. Okay, and due to that reason I cannot able to freely move in the space. Okay, now you can see that 0 is the minima of G, because if even if you will do this kind of construction f x alpha, and if I put g alpha equal to 0, at that time I have x0, and I have already defined x0 as a x star. Okay, so by construction of this I can tell that g0 is the minimum Okay, and due to that reason, exactly I can apply the same result, that this should be hold, g dash equal to 0 should hold. Okay, so now if g dash 0 should hold, then now I have to interpret the condition, because g0 is the parameterization, so I have to interpret same condition in terms of original curve, and due to that reason now I am going to take the differential on the both hand side. Okay, so if you take the differential of this, then gradient comes into picture, and after that I have x dot equal to alpha. Okay, so x dot alpha equal to comes into picture, and if I put alpha equal to 0, so since alpha equal to 0 is the minimum point, and we know from the unconstrained optimization that should be 0, so similar, because if you are at minima, okay, so you are in very vicinity of the that minima, and due to that reason this condition is satisfied, so this condition is obvious. Okay, apart from this I have to also generate some condition in terms of the constraint. Okay, so that kind of things now I am going to do. Okay, let us try to see here. The vector x dash 0 belongs to Rn is a important point, obviously, because I have constructed z alpha, that is f x alpha. Okay, and after that I am going to define g dash, that is the that I can that I have done like this, and x dash equal to alpha, and after that I have substituted alpha equal to 0. So finally what happens, that I have, and x0 is x star and x dash into 0. Okay, so now I am going to interpret this point, and due to that reason, and obviously this point is going to belong in Rn. Okay, so please be careful, x alpha that belongs to D, and D is subset of Rn. Okay, but if you are going to take the derivative, so I cannot able to make sure that that is also again going to lie in D. Okay, so it might possible some function is defined only in bounded region, but if you take their derivative, then they leave that region also. Okay, and but obviously that is not going to lie, or that not going to leave the whole space, and due to that reason now I am telling that x dash 0 when alpha equal to 0, that is going to lie in Rn. Anyone has confusion? Now what I am going to do, I am going to take the Taylor series expansion of that curve, okay, x alpha, and here you can see that in the previous slide I have already assumed that x alpha is at least one time continuously differentiable, and due to that reason I can able to write like this. Okay, so x dash 0 is just a linear approximation of x at x star. Okay, so geometrically if you see it, then I have some region D. Okay, and this is the minima point. Okay, and what I have done, I have parameterized, okay, or I have constructed that family of curve, okay, that is going to satisfy the constraint. Okay, and suppose constraint, after after seeing the constraint, and or after simulating the constraint, suppose this kind of a space comes into picture, okay, in Rn dimensional space. Okay, now here you can see that if you do the first order approximation, so x alpha I can interpret at the tangent at this particular point. Okay, so the vector x dash 0 is the tangent vector to D at x star. Anyone has confusion on this? Okay, it live in the tangent space to D at x star, which is denoted by tx star D. Okay, we are talking about tangent space, not only tangent. Why? Because I have some family of curve. Okay, so I have family of curve. Okay, x has n number of component. Okay, so if I am going to talk about the tangent, so again tangent also have n number of component. Okay, so some kind of a space is also going to generate using that vector. Okay, so this vector x dash 0, again that is going to generate generate some kind of a space, okay, where each column vector is represented like x1 dash 0, x2 dash 0, xn dash 0, okay, and due to that reason I have written here tangent space. Okay, now what we are going to do, we are going to 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 the characterize our result in terms of the equality constraint. Okay, so up to here what we have seen, that I have I have created some kind of parameterized curve. Okay, and after representing this parameterized curve, I'll end up to here x alpha, and after that, after calculating the derivative of this at alpha equal to 0, because alpha equal to 0 is my minima, so we'll end up to the this condition alpha, and after that x dot alpha. Okay, and by keeping alpha equal to 0, I have interpreted that what kind of things basically happens. Okay, now what we found, that this particular x dash 0 is the tangent, okay, that is going to form tangent space near to the minimum point. Okay, so tangent space that comes into picture at the near of this x star is minimum point in some region D. Okay, now what I am going to do, I am going to express this tangent space, and I am going to relate that tangent space with respect to the constraint curve. Okay, so you can see here that I have to make sure that this constraint is going to satisfy, and then I have to find the minima of some function fx. Okay, now what I am going to do, since this constraint is satisfied, so if I take the this constraint, and since if x alpha that is going to pass through this minima, so same time this x alpha also going to satisfy this constraint. Why I am claiming that? Because I have to make sure that x star is the minimum of function, and x star that will also satisfy the also satisfy the constraint. Now in order to make sure that x star that actually generated by keeping x alpha equal to 0, so I have to make sure that in the both side of x alpha, whatever constraint condition that should be satisfied. Okay, so whatever curve I am going to generate, that should satisfy the constraint too, and due to that reason, in place of x I can able to replace x alpha, and at the point of x alpha, h1 x alpha, h2 x alpha, and hm x alpha also should equal to 0, and due to that reason I have retained this condition. Anyone has confusion? So actually matter is very simple. I have fx as a some function, okay, and I have constructed some kind of curve, parameterized curve x alpha, and x alpha should satisfy the constraint. Due to that reason, in place of x I can able to replace x alpha. Okay, so please be careful, x and x alpha both are not the same. Okay, x alpha means I am going to parameterize whole curve in terms of some kind of a scalar, that is the meaning. Now since this equal to 0, so if I take the derivative with respect to that scalar alpha, that should also be 0. Okay, so if you calculate derivative, then this kind of things basically comes into picture, and when alpha equal to 0, then this condition should be satisfied. Okay, so we have shown that for any arbitrary c1 curve x in D with x 0 equal to x star, so in this way I have actually defined that curve. Okay, generalized curve, its tangent x dash must satisfy this kind of condition. Okay, so it means that in order to make sure that I have some space, I have some kind of function, and minima will satisfy this function as well as the constraint. Okay, now this condition should satisfy that this is gradient vector, okay, gradient of the constraint near to x star, okay, and this we have already interpreted that is tangent, their dot product should equal to 0. Okay, so could you please interpret this, anyone? What does it mean? If I have two vector and if their dot product equal to 0, then what is geometrical interpretation of that? Iram, could you please guess? If
Sir, they are perpendicular to each other.
yeah, they are perpendicular to each other. Okay, it means that x dash 0 that represent the tangent near to 0, and whatever constraint, gradient of constraint, that should be perpendicular. Okay, then only I can able to go for the minima, otherwise I cannot go for. Anyone has confusion? So this is the interpretation. We will see more transparent interpretation in the later slide. So I am going to give interpretation of now this condition. Basically, actually one can show that converse is also true. Converse is true means if you assume this, okay, then it is possible to show that this x star, whatever x star, if this condition is satisfied, then that x alpha near to alpha, that is going to satisfy the minimum condition x star and also going to lie on the curve. Okay, so that kind of condition is also satisfied. So I am not going to give the proof of that. Okay, just what I am going to do, I am going to apply the assumption. Okay, regular point assumption. What basically regular point assumption is telling, that regular point assumption is telling that near to x star all gradient should be linearly independent. What does it mean? That it means that if you take the tangent, okay, what basically we have to do, I have to make sure that I can move in both direction, and after that I can keep this point 0 as a minimum one. Okay, so basically if the regular point assumption satisfy, at that time if you calculate the gradient, okay, so all tangent vector is actually perpendicular to that. It means that I can move in both directions. That is the meaning, and due to that reason we are assuming that delta hi x star, okay, that should be linearly independent. If that is not linearly independent, it is possible to show that, okay, I cannot able to move in all direction and able to pick up. Because why all direction? Because here I am in r n dimensional space. Okay, so this condition, regularity condition, just telling us that I can able to move, okay, in any direction, such that the constraint, equality constraint will satisfy. Okay, so same kind of things I have written. In other words, the tangent vector d at x star are exactly the vector for which this kind of things hold. So this is the characterization of tangent space txd that we are looking for. Okay, so what happens, that suppose you have some kind of function, okay, and I have some kind of constraint. Okay, so function, minimum point of function I have to search, and at the same time I have to also satisfy the constraint condition. Okay, so now how to make sure that something is minimum, I have to see the value of this point. I have to go in each and every direction. Okay, and I have to make sure that this value is minimum. Okay, now since this is parameterized by some kind of a scalar alpha, so whenever some quantity is a scalar alpha, it means that somehow I can able to, I have to just move in two direction. Okay, so that is the beauty, that whenever we are parameterizing something with respect to alpha. Okay, so now this condition is equivalently that if I move in this direction and this direction, then all possibility is automatically checked and I can tell that this is the minimum. Okay, so it means that if this condition is satisfied, then Tx star D, that is D is nothing but, now you can see that here in place of D, in the previous slide I have written this as a x dash 0. Okay, now I am talking about the neighboring point of this. Okay, so neighboring point is represent all the tangent space. Okay, anyone has confusion, then please let me know. And same kind of things I have written now, that I can move in both direction. Okay, so using this kind of parameterization, now I can able to see whatever value that is neighborhood of all point. Okay, so most of time, since in the neighborhood I have infinite many direction, due to that reason after parameterization I have to just move in two direction. That is the beauty of parameterization. So most of time, whenever we are solving or we are parameterizing that curve, we are basically simplifying our problem. Okay, now let us move further, because I have two different conditions. Okay, so one condition that basically reflected when there is no constraint. Okay, now I have to make sure that constraint also satisfied, and after that function also should have minima. Okay, so if two conditions will satisfy simultaneously, then only I can tell that x star should be minima. So same kind of things now I am going to state here. So what I am telling, that now let us go back g dash equal to 0. Okay, and which tells us that again x dash 0, I have told you that x dash 0 is the exact point where I have x dash 0 is the tangent space. So I have represented this whole tangent space by d. Okay, this is parameterized by alpha equal to 0, so only by varying alpha I can move. Okay, and this d is basically lie in the whole tangent space. Okay, now what we have to make sure that this condition, okay, one condition in terms of function, gradient of function, neighborhood of this, and how basically I can decide the neighborhood. In order to characterize the neighborhood, I have to go through this tangent space. Okay, so I have to make sure that this tangent space, this kind of condition will satisfy. Okay, then only I can able to make sure that I am also x star is also going to lie on on the constraint. Okay, so due to that reason, these two condition is satisfied, then I can tell that x star is nothing but the minima. Okay, so this is the some kind of implicit version of proof. Okay, so now you can see that if what this condition is telling, suppose if you have some region D and if you have some kind of constraint surface. Okay, and then suppose if x star is minimum, then you have to generate the tangent space. Okay, and in this whole tangent space, this condition should satisfy. So this condition and this condition should satisfy. Okay, so this condition is very clumsy, very difficult to check, so we have to simplify it. Okay, so now second, so I have to eliminate D, because D, it means that whenever we are talking about D, then our result become very difficult to check, and due to that reason I have to characterize whole result in terms of known things. Okay, so what kind of things is known to me? I know the function, I know the constraint. Okay, so due to that reason I am going to express whole result just in the terms of the function and hx. If we are able to do that, then that result is detectable, I can able to check it. Okay, so next part I am going to do that only. Okay, so what we are telling, the gradient of f at x star is the linear combination of gradient of constraint function this. Okay, so this I am going to prove that delta fx star in the span of this. Okay, so if we are able to prove this, it means that now I can able to represent, if this point lie in a span of this, it means that these two are linearly dependent. Okay, this whole things and plus these things are linearly dependent, sorry, these two, because span I am talking about. It means that suppose if you are in two-dimensional space, you don't know what is this point. Okay, but if we are able to understand that this point can be represented in the combination of these 2 points, okay, means this point is going to lie in the span of 1 0 and 0 1, so I can able to represent this point just by multiplying x and y. Okay, so this kind of claim I have done, and I am going to prove this claim. Okay, and again, in order to prove this, I am going to use the idea of the proof by contradiction. Okay, so what I am going to do, first I am going to assume that delta fx star, first I have to prove this, that delta fx in the span of this. So I am going to assume that delta fx would have a component, at least one component, that is orthogonal to that span. Okay, it means that what I am going to do, suppose that I have to prove this point in this space. Okay, so if this point will not lie in this space, so I will tell that okay, there exists a third space that is perpendicular to that, there that is going to lie. Okay, so that kind of things I have written. It means that again, but I have to make sure that this condition should satisfy always. Due to that reason, this condition is satisfied for all I equal to 1 to m. Okay, now since if this is not going to lie in the span of this, so I can able to write like this. So a span of this all quantity d, here you can write as a minus plus, that doesn't matter. Okay, now what I am going to do, I am going to take the inner product. So if you take the inner product, so this from this, that equal to 0, so delta fx star dot d, that d square, but I have to make sure that that should be also 0. Okay, because from here this condition is telling that both things should be 0. But what kind of condition I have comes into picture, if that is not lie on the span? Okay, it means that something in perpendicular. So just by vector addition I can write like this vector plus this vector equal to this vector. Okay, so due to that reason this condition basically comes into picture, and after that by taking inner product, okay, whatever condition I have actually seen here in this condition, that should be violated. It means that if we assume that that is not in a span, then some contradiction comes into picture, and due to that reason, by contradiction I can tell that that should be lie in the span of this. In this way we can prove this. Okay, so once this result is proved, then now let us come to the geometrical interpretation of this. So geometrical interpretation is like this. Suppose that I have some curve fx. Okay, and what happens that I have some region d, and I have find x star. So here I have x star in this region. Suppose this is the region d. Okay, now for simplicity what I have done, I have just going to assume that I have two constraints. One constraint is h1 and another constraint is h2. I have just two constraints. Okay, so try to move one by one. Suppose if you have some function f x that going to lie in d, and d belongs to Rn. Now if you have just one constraint, okay, so if you have just one constraint, then what kind of things happens, that delta fx comes into picture and delta h1 comes into picture. Okay, and you have to make sure that delta hx and delta fx, that is lie on the span. Span means now all are going to lie in the same plane only. Okay, if you add one more, then that is again going to lie on that particular span. Okay, so and this thick curve is nothing but curve of the constraint. Okay, so we have to make sure that trajectory, if trajectory will move in this means some plane kind of things basically comes into picture. So in this direction, in every direction, then this should be minimum value. Okay, so geometrically what happens, that in order to make sure that I can move in all direction, whatever gradient vector that comes into picture all should be perpendicular. Either that is gradient vector of function, or either that is gradient vector of this particular constraint, okay, near that equilibrium point. Okay, then only I can tell that in any direction I can move, and after that I can find the minima. So same kind of things basically I have written here. Note that if there is only one constraint, then this kind of situation is there. When you add second constraint, then basically you will get the plane. So in whole plane I have to check that that is the minima. Okay, now similarly, in general, the intuition behind the claim that unless delta fx star is the normal to D, there are curves in D passing through x star whose tangent x star make both positive and negative inner product of delta fx. Hence, in particular, f can be decreased moving away from the x star. Okay, so if you see the inner product with help of inner product I can able to define the norm, and norm is nothing but they are telling that some kind of distance. Okay, so suppose if something is minima in higher dimensional space I am telling, so and suppose some curve is also passing. For example, you can take a straight line of this curve, so you have to make sure that here if I move in all direction, okay, or suppose this plane is touching, so you can keep ball on this plane, and after that you have to find the minima of this function. So obviously that minima should be lie on the bottom of that only. Okay, so that will satisfy this. So all perpendicular means all gradient at this point. Okay, so this side gradient should be means because I have to decrease in this direction, I have to decrease this direction, so that should be opposite direction. Okay, so I have to make sure that all gradient of this particular constraint and gradient of this all are lie in the same plane, and due to that reason if that is on same plane, so I can write in a span in form of a span means that is linearly dependent. And if something is linearly dependent, it means that there exists a lambda 1 lambda m and all are non-zero such that I can able to make sure that equal to 0. Anyone has confusion? So we have, when I have started the lecture at that time I have defined linearly dependent. Okay, so linearly dependent means I can now able to find lambda 1 star, lambda 2 star, lambda m star that is non-zero such that this condition should satisfy, or at least one lambda 1 that should be non-zero, like that. Okay, so now in order to find that x star is the minimum, okay, or local minimum, just I have to make sure that this condition should hold. Okay, and for that you can now see that what kind of restriction basically comes into picture, that delta x of gradient of f should exist, gradient of h1 that should exist. So due to that reason I have assumed that kind of situation. Okay, now why I have assumed that delta h1, delta h2, delta hm all are linearly independent? If I do not assume that, then what happens, that one constraint will not satisfy. It means that I cannot able to make sure that I am going to lie on that particular curve. Okay, due to that reason, now even if you can see that this and this whole quantity, because this is written in the linear combination of this whole quantity, but this quantity delta h1, delta h2 all are linearly independent. Okay, so I'm not telling that this and this whole quantity is linearly dependent, but this should be linearly independent. Okay, then only whatever constraint I can move in all direction of constraint as well as on the curve. Okay, now let us try to see the some more simple condition. So this condition should be satisfied. So this is the first order necessary condition. And why first order? Because whatever curve I have created, and after that I have taken the first order approximation of this curve. Okay, and based on that only I have generated this kind of condition. Due to that reason first order means necessary condition that comes into picture. Okay, now what I am going to do, I am going to represent this first order necessary condition in more simpler form. Okay, and there idea of Lagrange multiplier comes into picture. Okay, so what Lagrange multiplier is basically telling, since in this particular problem I have some kind of curve that belongs to Rn, I have constraint that belongs to Rm. So basically I have n plus m unknown. Okay, n unknown if I want to find x star, and m unknown. So you can assume that I have n plus m unknown. Okay, so now whenever constraint comes into picture, then simply dimension is going to increase. Okay, now meaning of the minima that I have x star, and apart from x star I have lambda 1, lambda 1, lambda 2, lambda m. Okay, so m number of independent vectors I have. Okay, now what I have to do, I want to apply same result of unconstrained case. Okay, so at that time what we have seen here, that whenever I am talking about the minima, at that time I have to make sure two condition. Okay, in now I am telling that how to make sure using one condition such that two condition explicitly comes into picture. Okay, due to that reason now I am going to modify the function. So initially I have original function fx. Now I am going to, whenever I have constraint, I will multiply with some constant. Okay, lambda 1, lambda 2, lambda 3, lambda m, and after that I am going to calculate the augmented cost. Okay, and in this augmented cost you can see here that when lambda 1 star, lambda 2 star, lambda 3 star that comes into picture, and f is x star, at that time since constraint is satisfied, so due to that reason this term is 0, and due to that reason this become x star, because when x at x star, this value, all value equal to 0, all constraint is satisfied, so that all equal to 0, that is already 0. Due to that reason now what happens, whatever minimum of this, that is exactly equal to x star. So due to that reason I have defined the augmented function now, and after defining the augmented function, now what I am going to do, if I have some kind of function, and we know that whatever function I have defined, their rate of change g dash, that should equal to 0. So same kind of condition actually I have applied here. Okay, but what happens whenever you are going to define the augmented function, at that time two different variable involved now, x and lambda. Okay, so you have to make sure that partial derivative with respect to x, that should be 0, and partial derivative with respect to lambda, that should also be 0. Okay, so now this equal to 0, it means that this condition is also satisfied, this first condition, and after that this condition is also satisfied. And you can see that when I have talked about whatever result I have derived just before, we are telling that delta fx is a span of this, and due to that reason this condition is again comes into picture. Okay, so now in order to solve this, the constraint optimization problem, there is no need to worry. Okay, what you can do, you can take your function, whatever equality constraint, you can multiply that equality constraint with some kind of lambda. After that what you can do, you can find the some kind of augmented function, and now you can take the partial derivative of the augmented function with respect to both variable, and just keep it as equal to 0. Okay, so obviously since hx should already always satisfy, means x star, because I know that constraint is always satisfied, means minima should also satisfy the constraint. Due to this reason this result is obvious, means hx star is 0. Okay, so that is obvious, and obviously this result basically comes into picture. Okay, so first systematically you have to derive it, and after that you can tell that if I just modify the cost, okay, or if I just modify the function, okay, then I can land up to the same result. Okay, so in this way I can tell that whatever modification I have done, that is correct modification. Due to that reason, first I have come up with the original function, I have actually parameterized that function, same like the unconstrained optimization. Since here I cannot move in any direction, I have to move and take care that always whatever constraint that also satisfies. So what I have done, I have generated the tangent space. Okay, tangent space actually gives us the way such that I can move, and after that we have formulated the result. Okay, I hope that you are able to understand the idea. Okay, now let us come to the second order necessary condition. Okay, so in order to define second order necessary condition, now a story is very simple. Okay, because what we have seen so far, that I can convert my constraint problem into unconstrained problem just by adding the Lagrange multiplier. So same kind of things you can do. Okay, you can first define the augmented function. Okay, and now what you can do, whenever we are talking about the second order necessary condition, at that time we are talking about the second order derivative. Okay, second order partial derivative. So same kind of things you can do. Okay, and at that time we are assuming that first order condition should be satisfied. Okay, this condition should be satisfied, and then we are taking it means that we are also making sure that f dash should equal to 0, and after that we are looking for f double dash. Okay, so similar kind of things you can do here. So in the previous class Hessian matrix comes into picture, so same kind of matrix basically comes into picture. Now what you can do, if you write in terms of positive definite matrix or positive semi-definite matrix, same like previous, then this kind of condition is comes into picture, and you have to make sure for all tangent space that should be satisfied. Okay, so again this is not very easy job, you have to check for all point. Okay, and now since this is second order necessary condition, and in previous class what we have found that first order necessary condition, second order necessary condition, if you dilute or strict the second not dilute, strict the second order necessary condition, then that become the condition for local minima. Okay, and that is now sufficient condition. So first necessary condition, that is coming from first order approximation, and second sufficient condition is basically coming from second order approximation, but at that time we have to talk about a strict inequality. So you can see that just I have changed the inequality, so a story remains exactly the same. Okay, so now it is time to conclude the today's lecture. So what basically we have seen in today's lecture, so that if I have some kind of real valued function, if some equality constraint comes into picture, okay, then we are defining Lagrange multiplier. Okay, and we have, and using Lagrange multiplier we are defining some kind of augmented function. Okay, so now most of time what happens, that people are doing this kind of exercise, but they are not knowing that why they are doing this exercise. So we are trying to identify that why basically we are doing this kind of exercise. So in order to understand that, what we have to do, first we have to understand that whenever constraint case comes into picture, then what kind of restriction comes into picture. It means that I cannot move freely. Okay, so I have to move in such a way such that constraint curve also satisfy, and whatever function that should also satisfy. So two things should satisfy together. Okay, so in order to satisfy two things, I have expressed the condition in terms of the gradient, and what we found that gradient vector of f, okay, that should be lie in the span of the gradient vector of, or linear combination of gradient vector of the constraint. Okay, so all possible constraints should satisfy, and due to that reason I have to make sure that gradient vector of all constraints that should be linearly independent. Okay, so if that is not linearly independent, then I cannot able to cover all the constraint. Okay, and due to that reason regularity assumption comes into picture. Okay, so if we believe on regularity assumption, okay, so then it is possible to show that whatever constraint I have, suppose if regularity means condition is fail, then again I cannot able to solve that problem. Okay, it means that it might possible that whatever minima we are going to generate, that may or may not occur. Okay, so due to that reason I have to check the regularity condition, and once regularity condition is fulfilled, then now story is very simple. Okay, what you have to do, you have to define augmented function, and now whatever way you are solving unconstrained problem, same way you can able to solve it. Okay, so this is the story of the today's lecture. Okay, so since you all are master and PhD, due to that reason, what I am requesting to you, please go through the proof too. Okay, then you are able to understand that why things are working, why things are not working. Okay, so now class is in from my side. If you have any specific question, then please let me know from the today's lecture. Okay, if you don't have any